Bismillahirrahmanirrahim. Our new chapter starts magnetically coupled circuits, and in this chapter we cover the topics self-inductance, self-inductance, mutual inductance, energy in coupled circuits, energy in coupled circuits, linear transformer, linear transformer, ideal transformer, ideal transformer, ideal auto transformer, ideal auto transformer. What is auto transformer? Auto transformer which has only one winding, and that one winding shares both the sides, that is primary and secondary. And finally, three phase transformers. Three phase transformer. So in this chapter we cover these topics. So what are the learning outcomes for studying magnetically coupled circuit? The learning outcomes are to understand the basic concept of self-inductance and mutual inductance, to understand the concept of coupling coefficient and dot determination in circuit analysis, to understand the direction of magnetic field lines by curl the fingers using your right hand. It will be tell you. I will tell you in later to later. I will tell to you later, and to understand the dot convention for EMF induced polarity. So these are the learning outcomes. I will share my slides also. So you can see in the slides, everything will be explained. Means if you want to see the wordings, you can go through my slides. Now students start from self-inductance, or simply start from inductor. This one is inductor. This is voltage induced in inductor is LdI by dt. For example, a sinusoidal volts, that is supply is given to inductor, sinusoidal volts. In result of sinusoidal supply, a sinusoidal current will flow through the inductor. In result of sinusoidal current, a sinusoidal flux will be set up in the inductor. AC supply, that is sinusoidal. Due to AC supply, AC current, that is sinusoidal. Due to AC current, AC flux, that is sinusoidal flux, time varying flux. So what is inductance? What is voltage induced in the inductor? It's L times. L times means Henry's rate of change of current with respect to time. So in previous live session, most of the students asking about why inductor does not allow abrupt change in the current. See the inductor equation. Rate of change of current. If you want to abrupt change, means if you give DC to inductor, it behaves like a short circuit. If you give DC to inductor, it behaves like a short circuit, because if you want to change the inductor current in zero time, you have to have infinite voltage at inductor terminals. If you want to change the inductor current in zero time, you have to have infinite voltage inductor terminals, and that is impossible. So that's why inductor opposes the change in current, right? Why it opposes? Because due to due to change in current, that is when this one is inductor, this one is current, right? And this one is AC current. So this flux is set up, right? Flux is set up. This flux links itself, right? The time varying flux links itself the coil and induced a voltage. induced a voltage, right? Which is minus n d phi by dt. Does it mean? Rate of change of flux with respect to time and number of turns. It induces a voltage which opposes its cause, that is supply voltage. It is opposite to its cause, that is supply voltage. So induced voltage opposes its cause, that is supply voltage. That's why it opposes change in current, right? Because this one is induced voltage, and according to Lenz's law, it opposes to supplied voltage, right? So due to this property of induced voltage which causes opposes, that is applied voltage, this induced voltage in the inductor, it opposes supplied voltage. Due to this property, it changes the rate of change of current, and the rate of change of current depends upon rate of change of flux actually, right? Di by dt, that is rate of change of current with respect to time. D phi over dt means rate of change of flux with respect to time. And number of turns, it depends on the number of turns of the coil. See, number of turns of the coil, right? Amount of current flow in the coil, and that amount of current flow, that is induced voltage. This minus sign showed to you Lenz's law, right? This induced voltage is nothing but minus n number of turns of the coil, rate of change of flux with respect to time, right? So that induced voltage is, this negative sign shows to you Lenz's law. It opposes its cause, that is, it opposes a supplied voltage V. Now let's also discuss the behavior of the capacitor. How capacitor behaves. This is capacitor, right? C. So capacitor current is equals to C dVc over dt. Capacitor current is equals to rate of change of voltage of the capacitor with respect to time. So you cannot change the capacitor voltage abruptly, right? Abruptly. So if you want to change the capacitor voltage abruptly, you to have a capacitive current infinite at the terminals of the capacitor. Infinite current. You need infinite current, because if you want to change the voltage of the capacitor in zero time, derivative of zero is zero, right? And something over zero is infinity. So you need to have an infinite time of infinite amount of current to flow in the capacitor to change its voltage abruptly. So it opposes abrupt change in voltage. That's why in capacitor current leads, right? Current leads. Current comes first, then voltage in capacitor. Why? Once AC, and it also it only allows AC quantity. See, rate of change of voltage with respect to time, AC quantity. So what happens actually when AC current flow, capacitor for the timing being act as a short circuit, and then electrostatic field is stored in the capacitor. Electrostatic field. Remember, in inductor it was electromagnetic field. Electromagnetic field. In capacitor, electrostatic field. In inductor, voltage leads the current. See, inductor equation, VL is equals to LdI by dt. Inductor equation, voltage leads the current by 90 degree in pure inductor. In capacitor, pure capacitor, current leads the voltage by 90 degree. See the equation of the inductor and capacitor. On the left hand side, the dominant is voltage. In capacitor equation, the left hand side is current, right? So very easy to remember. In capacitor, current leads, current comes first, then voltage. In inductor, voltage comes first, then current, right? Okay, now we study self inductance. Now come towards the mutual inductance, right? When there are two coils in a close proximity, that is two coils, for example, one coil and second coil, right? Two coils, and we are given supply to primary side, that is this side. Supply is given, right? A current will flow in the first coil. That current flow induces a voltage in it itself and that flux also links with its neighboring coil and induces a voltage in the neighboring coil. So this one is mutual inductance, right? Change of current in one coil induce voltage in the second coil, and vice versa. Vice versa means, see, supply is given to this coil, current is flow. See, a flux is links with itself, and the flux is links with the secondary coil. Vice versa means supply is given to one coil, and voltage is induced in the neighboring coil. So when supply is given to one coil, the voltage induced in the neighboring coil is mutual inductance, right? And this one is self inductance. It links itself and induce a voltage in it, right? So this one is self, this one is mutual. So if we draw the circuit and drive a simple equation, so just you need to instantaneous current I with respect to time, instantaneous current, it flows into a coil, it flows into the coil, and let's suppose the voltage induces like plus minus V across the coil, and it sets up its flux, it sets up its flux due to AC current. The flux is set up, right? The flux is set up, and let's suppose the flux direction is like clockwise, right? The flux direction is clockwise. In the vicinity of this coil, there is no other coil, so this flux is leakage flux. Actually, it does not link with the other coil, right? So voltage of this coil is nothing but N times d phi by dt. Number of turns of the coil, rate of change of flux with respect to time. The voltage induced in the coil is nothing but N d phi by dt, and we know that V is equals to what was the cause of this flux? The cause of flux was di by dt, right? D phi by dt is the causes di by dt. Rate of change of current with respect to time produce a rate of change of flux with respect to time. Okay, so V is equals to, and we know that this one is uh, this one is inductance L, right? So V is equals to L di by dt. So L comes out to be N d phi by dt, right? Now we consider two coils. Two coils. Now we consider two coils, that is coil 1 and coil 2. So let's suppose the instantaneous current I1 times T flow in one coil, and voltage is induced at the terminals of the first coil, that is V1, and flux is set up due to its primary current, that is phi 1 1, right? This flux set up in itself, right? Not neighboring. And the flux is also set up in the neighboring coil due to change in current in first coil, that is 1 2. Flux set up in neighboring coil 1 2. And induced voltage in the neighboring coil is such that plus minus V2. And this one is L1, this one is L2. Coil 1 self inductance, coil 2 self inductance. L1, this one is L1, this one is L2. So what is the flux? Total flux? Self plus mutual. because this coil set up two flux. One is self 1 1, that is due to change in current first coil, self induced, and due to change in change of flux in primary coil, induced voltage in the secondary coil. So flux 1 2, right? The addition of both becomes total flux. So what becomes V1? V1 is nothing but number of turns of N1. These are number of turns of N1. This one is number of turns of secondary coil. There are two coils. So number of turns of primary is N1, number of turns on secondary is N2. So voltage induced in primary is nothing but N1 times d phi 1 over dt, and voltage induced in secondary coil is nothing but N2, number of turns on secondary coil, rate of change of flux in secondary coil divided by time. Phi 12, in fact phi 12, yes. This flux is phi 12. Change in current in first coil induces a voltage in the secondary coil. See, so V2 becomes this. So again, you can write like this: V1 equals N1 d phi 1 dt, N1 d phi 1 dt, and di1 dt is equals to L1, because this one was L, right? L1 L1 di1 over dt, right? Where L1 is equals to N1 d phi 1 by dt, you can replace in this equation this parameter by L1. Similarly, you consider equation 2, that is this one is equation 2, this one equation 1 named, this one equation 2 named. So consider equation 2, V2 is equals to nothing but N2 times d phi 1 2, mutual inductance on coil 2 due to coil 1 1 2, right, over dt, and this mutual because of rate of change of current in primary coil, that is di1 by dt. So we can write this term as a mutual term. We can write this term as a mutual term, that is M1 M21. The mutual term becomes M21. The mutual of primary on secondary, right? The change in current in first coil, mutual inductance on secondary coil. 1 on 2, M21. M21, right? So that M21 equals M21 equals nothing but N2 by d phi 1 2 over dt. So the secondary voltage was V2. I'm writing again, N2 d phi 1 2 over dt, di1 over dt equals M21 times di1 over dt. This term is M21, right? This one is M21. So M21 is known as the mutual inductance of coil 2 with respect to coil 1. M21 is a mutual inductance, of coil 2 with respect to coil 1. Subscript 21 indicates that inductance M21 relates the voltage induced in the coil 2 to the current in coil 1. Thus, the open circuit mutual voltage or induced voltage across coil 2, that is V2, equals mutual inductance M21 times the change in current in coil 1, right? The voltage induced in this. Now, vice versa. Let's suppose that you have two coils. That is, you have primary coil and you have secondary coil. But this time, you are going to supply secondary coil. You are going to supply secondary coil with an sinusoidal current. That is I2 times T instantaneous current in the secondary coil. This one is open circuit voltage, right? There is voltage induced due to change in current in first coil. So this one open circuit voltage on primary side. This one is V1, this one is V2, right? This one's the opposite. So now consider this case. You have a coil L1, coil L2. You have voltage induced in coil 2. In this case, supply is given to coil 2, and open circuit voltage appears in coil 1, V1. So this time there are two flux, self-induced flux, that is change in current in primary coil, induces a voltage in the coil, and change in current in primary in this coil, that is coil 2, induces a voltage in the secondary coil. So that one is this mutual, this phi 2 1, so subscript 2 1, that is change of current in secondary coil induced a voltage in primary coil. It is opposite. Before it was phi 1 2, now is phi 2 1. So there are number of turns on primary side, let's say N1, number of turns on secondary coil, let's suppose N2, and what is the total flux? Phi 2. Phi 2 is phi 2 1 plus phi 2 2. Total flux remains phi 2 1 plus of phi 2 2, and the entire flux phi 2 links coil 2, so the voltage is in the coil 2. So the voltage induced in coil 2 is nothing but number of turns on coil 2 and number of flux lines on coil 2. So we can write like this, that is N2 d phi 2 by dt, and this due to secondary current, this voltage induced due to secondary current, that is I2. So finally it becomes L2 times di2 by dt. So so we may write that where L2 is nothing but N2 times d phi 2 over dt, oh sorry, over di2, and it is a self inductance of coil 2. It is a self inductance of coil 2. See, all the quantities involved are coil 2 quantities, so self inductance. So finally, what was the V1? V1 was N1 d phi 2 1 over dt is equals to N1 d phi 2 1 over di2 times di2 over dt is equals to M12 di2 over dt. So M12, that is mutual inductance of coil 2 on coil 1, is equals to N1 times d phi 2 1 over di2. So V1 equals M12 times d phi the di2, sorry, di2 over dt. So we conclude M12 equals M21 equals M. Mutual inductance of on coil 1 due to secondary current, mutual inductance on coil 2 due to primary current. And finally, we designate as M, that is mutual inductance. So mutual inductance is the ability of one inductor to induce a voltage across a neighboring inductor measured in henries. We know the unit of inductance. Inductance are measured in henries. You can see the clear definition in my slides. I will share my presentation PPTs also, so you can see over there. Thank you. Bismillahirrahmanirrahim. Now we see the magnetic flux direction. That is, we use our right hand to see the direction of the flux, right? Magnetic flux line. Consider this one as a core. This one is core, right? This one is wire. So you have to wound the core, this wire. You have to wound on the core. See, these are the number of turns. See, number of turns. You are wounding the core. You are wounding the coil on a iron core. This one is core and this one is coil. You wound on the core, right? So one way is to wound the core from top to bottom. You start winding, wound from top to bottom. See, the core, the construction of winding is from top to bottom. One way is to wound the core, that is same, but this time from bottom to top. That is you reverse it from bottom to top. You wound the core. You see, these are the windings. These are the windings of the coil, right? Top to bottom and bottom to top. So in this case, you have two coils. See, current will flow in the terminals. These are the terminals of the coils. See, this is the coil, right? So terminals of the coil and current flow, right? Current flow from the top to bottom. Current is entering in the coil from the top terminal and leaving from the bottom terminal. In the second example, you see current is entering from bottom terminal and leaving from the top. See, current entering from the bottom and leaving from the top. In both the cases, the direction of magnetic flux lines, note this one. The direction of magnetic flux lines is, in this case, the magnetic flux lines are upward, current is downward. In this case, the correct direction of current is upward, while the magnetic flux lines are downward. The example is when you drive the car, your car goes in one direction, that is forward direction. The smoke of the car comes backward in the backward direction. The example is this, right? Okay. Now we use our right hand. We use our right hand to and curl the fingers in the direction of current flow. So for this, let's see this example. The current comes from the top of the coil and flows towards downwards, right, in the coil. See, same example. We take this as a core and we start wound the core. Wound, right? See, winding. We wound the core. This one is winding. This one is winding, right? And the current flow from the top to bottom. So we right hand, we use our right hand, okay, and we curl the fingers in the direction of current flow of that coil. See, the current flow from top to bottom. So current flows like see. So we curl the fingers in the direction of current flow. Current flow, we curl the fingers. So take the example of this current flow. See, the current flow from top to bottom. So put your right hand and curl the fingers in the direction of current flow. See, my thumb is upward. So thumb gives you the direction of magnetic flux lines, right? Thumb will give you the direction of magnetic flux lines. In this case, the magnetic flux is upward. Now consider the second example. In second example, see, the current enters from the bottom of the coil instead of from the top, right? So for this case, again, consider this coil, right? Consider this coil, and you give the supply to the coil, and this time the current flows. See, current goes upward, right, from bottom to top. So again, you use your right hand, and you curl the fingers in the direction of current flow. So the current is going like this, right? So when you insert your right hand and you curl the fingers in the direction of current flow, your thumb will point out the direction of magnetic flux lines. So in this case, the magnetic flux lines are downward. So we concluded that when we change the current direction, the magnetic flux lines also changes its direction. That is, magnetic flux is also opposes due to change in current, due to direction of current changes, right? For the sake of simplicity, you may consider the diagram like this. Before it was in the, now consider this diagram. In C, the current is entering. Sorry, I1. I write I2. The current is same. That is I1, but it flows from bottom to top, right? So its magnetic flux lines are top to bottom. Phi 1, right? Magnetic flux lines are. So again, you insert your right hand, right hand, and curl the fingers. Sorry, like you insert the right hand and curl the fingers in the direction of current flow. The thumb will point out the direction of magnetic flux lines. I hope you understand.